We're all constantly making judgments based on pretty limited information. But how do you make the smartest possible guess when the data you have is, well, kind of sparse or even a little bit noisy? That's where this really powerful statistical idea comes into play. It's called Maximum A Posteriori estimation, or just MAP, and we're about to break down exactly how it works.
Okay, let's kick things off with a little puzzle. Imagine you flip a coin 10 times, and it lands on heads 8 of those times. So what's your gut reaction? Do you think this coin is seriously biased, or did you just happen to see a lucky streak? Your answer to this question, it really gets to the very heart of the whole dilemma we're digging into today.
And this brings us right to our first section, the data dilemma. Because, while it's super tempting to just let the data speak for itself, the most obvious answer isn't always the right one, especially when you don't have a whole lot of data to go on.
Now, one way you could try to solve our coin problem is with a method called maximum likelihood estimation, or MLE for short. The easiest way to think about MLE is as the just the facts approach. It looks only at the data you collected and asks a really simple question. What value, in this case, what level of coin bias would make the outcome I just saw the most likely?
So, if we just follow the logic of MLE, the conclusion is totally straightforward. The most likely probability for heads is simply 8 out of 10, which is 80%. But, does that feel right to you? Your real-world experience is probably screaming that a coin being that biased is, well, it's pretty darn rare. Our intuition is basically telling us that something is missing from this picture.
And that thing that's missing, that's where MAP comes in. See, unlike MLE, which can jump to some pretty extreme conclusions with small data sets, MAP takes a much more balanced, more robust approach. Why? Because it considers something else, something beyond just the raw data. In fact, MLE is really just a special case of this bigger, more powerful MAP framework.
So, what is this something else that MAP is looking at? Well, this next section is all about that secret ingredient. This is the part that gives MAP its real power, the thing that lets us blend our real-world intuition with the hard evidence right there in our data. And that secret ingredient, it's called a prior belief. This is just a fancy way of saying, what did you think was true before you saw any of the new evidence? For our coin problem, our prior belief is simple. Most coins in the world are fair, or at least really close to a 50-50 split. We don't start from zero, we start with that general knowledge.
So let's look at the math really quick. MLE is all about this one term, P of data given theta. All that means is what parameter, what theta, makes the data we actually saw the most probable. Notice the only thing that matters here is the data itself.
But now, look at the MAP formula. It starts out the exact same way, but then it adds this crucial new piece, P of theta, our prior belief. So the key is this. MAP isn't just maximizing the likelihood of the data, it's maximizing the likelihood of the data combined with the likelihood of our prior belief. It's a total balancing act.
And this quote just nails the effect. MAP takes that extreme 80% guess from MLE and it gently pulls it back toward our prior belief, the idea that the coin is probably fair. So the final answer is going to be somewhere in between, maybe 70%, maybe 75%. It's a much more reasonable guess given we only flipped the coin 10 times.
Okay, so this is a pretty neat statistical trick for figuring out coin flips, but why does it really matter today? Right, let's shift gears now and reveal the deep connection this has to the world of AI and machine learning.
It's a totally fair question. This whole concept is rooted in Bayes' theorem, which is from the 1700s. So why on earth are we talking about it now, in the age of giant neural networks and large language models? What makes it so incredibly relevant?
Well, here's the big payoff. MAP estimation is actually the statistical engine that powers one of the most important concepts in modern machine learning, regularization. Regularization is what we use to stop our AI models from basically overthinking the data they're trained on, a problem we call overfitting. It keeps them from making wild, crazy predictions based on very limited evidence.
And this connection is not just some vague idea. It is explicitly mathematical. If you choose a specific type of prior belief, it's mathematically the same as using a specific type of regularization. So for example, assuming your parameters follow a classic bell curve, that's a Gaussian prior, is exactly the same as using something called ridge regression. And assuming a spikier Laplace prior, that's the same as using lasso regression. These are absolute cornerstone algorithms in machine learning.
This quote just says it all. When a data scientist adds a regularization term to their model to stop it from overfitting, what they're really doing, whether they even realize it or not, is applying map estimation. They are injecting a prior belief directly into their algorithm.
So let's start to wrap this up by looking at why map is such a pragmatic superpower in the real world. This isn't just some elegant theory. It's a seriously useful tool for building better, more reliable systems.
So why do people reach for maps so often? Well, first, it directly fights overfitting. It also lets us formally build expert knowledge right into our models. It gives us stable, sensible answers even when our data is sparse. And, this is a big one, it's computationally practical. We can actually calculate it without our computers melting down.
Now, it's important to know that MAP isn't the whole story. It's got a more complicated, more intense cousin called full Bayesian inference. But where full Bayesian methods give you this whole range of possibilities, which is definitely more complete, they are often incredibly slow and complex. MAP, on the other hand, just gives you a single best guess. It's fast, it's efficient, and it's more than good enough for a huge number of real-world problems.
Honestly, a great way to think about all this is to imagine you're tuning an instrument. If you only listen to the raw evidence, the sound of the strings right now, you might tune it way too sharp, basically overfitting to the noise in the room. But if you only trust your prior expectation, where the tuning pegs should be, you're just ignoring what the instrument actually needs. MAP is the art of listening to both to find that perfect harmony. And that leaves us with one final thought. We've seen that so many of our most advanced algorithms are, at their core, just balancing prior beliefs with new data. So the question to really think about is this: what invisible assumptions, what priors have been built into the AI systems you interact with every single day? What beliefs are out there quietly shaping your world?